are down to our sixth class and last class for today. We are going from now until I guess just after 6 o'clock. And the last class today is talking about the SPI device driver. And we'll be going over the subsystem and some examples and some demos and even blinky lights and all sorts of neat things. So Michael Welling is your instructor for this section, and he will be taking it from here. Thank you very much, Michael.
So as being said, my name is Michael Welling. I am the founder of QWERTY Embedded Design, which is a small contracting company. But it's pretty much me and my wife. She does the books. So today we're going to cover SPI, and so I'll go through and talk a little bit about SPI first. And then after we get a little bit of background on SPI, we'll start talking about the Linux subsystem, a little bit of history, how the drivers work, and then from there we'll go on to the examples and labs, etc. So SPI is a serial protocol, and it's full duplex synchronous serial. So that means that it communicates in both directions simultaneously, and it's a pretty old standard, a de facto standard created by Motorola in the early 80s. I2C was actually invented at pretty early 80s too, I think. So there's usually one master on the bus and then a series of slaves. Each slave is assigned an address using the chip select pin. So let's go through the pins on the protocol or on the hardware. First, you have this serial clock, which is just a synchronous clock. You have MISO, which is master in, slave out. So that'll send data out from the slave into the master. Then you have master out, slave in. Chip select is how you address the chips on the bus. So when the chip select toggles low, that's what the end means, or usually there's a bar over the top of the chip select name. That just means that when that line toggles low, you're addressing that specific bus or that specific device on the bus. Occasionally you'll have other lines like interrupts and maybe some pin strapping for modes, and it's really these are the first four are the core things for the protocol. Okay, so here's a picture of kind of a slap together picture for, sure. What's that? We should probably get the mic first, yeah.
Sorry if you have this on your slides. What drives SCK?
SCK is a clock, and it's driven by the master side. Yes, it's a synchronous clock. So the master will drive that clock, and it'll go out to all the slaves, and will all use the same first 3 lines there. They'll go to all the slaves. It's not really well represented here, but it'll actually fan out to all the slaves on the bus, and then for each slave you have a chip select that'll toggle for each one that you want to address. Okay, and there's a lot of SPI devices out there. Here are some examples that you'll find pretty common. You got your analog converters, sensors, inertial and temperature, etc. Then you got you could have serial LCDs, either graphical or like character. There's a couple of those out there. You have SPI flash, which is pretty common, used on a lot of devices for boot, actually. Touchscreen controllers. FPGA programming interfaces is an interesting one because a board that I designed uses the ICE40 FPGAs, which are programmed through SPI, actually. Okay, so SPI has a couple of modes, like 4 modes. Based on a couple of parameters, which will change the clock polarity and phase based on the setting. So C-pole is the clock polarity, and it really just tells you how the clock, the state of the clock when it's not active. So when the C-pole is set to 0, the clock will idle low when it's not under transaction. If it's 1, then it'll idle at high. Then C-phase just determines which clock edge will do the latching and which will do the output. So I'm going to show some waveforms of this. So if it doesn't make sense in text form, maybe it will with the waveforms. Typically, the modes are represented in either tuple form or encoded as modes 0 through 3, which is just the binary encoding or decimal. Okay, so here are the waveforms for the different modes, so you can get an idea of how the clock and chip select, MISO, MOSI will interact during different modes. So mode 0, the most common mode, you'll see as the data is there on the rising edge of the clock, and then it'll transition on the falling edge. So the polarity is 0, so the clock is going to stay at 0 when it's not being accessed. If your polarity is 1, you'll see that the clock stays high when it's not being accessed. And outside of the chip select frame, this isn't really guaranteed because you can have multiple devices on the bus. So as soon as the chip select goes away, the clock can go to either state. It's just a matter of having it in the right place before the chip select occurs. And you'll see with the phase, you'll see that the data kind of shifts that way, and it just the transition on just different sides of the clock and different polarity of the clock, essentially, or phase of the clock. So those are the 4 modes. Okay, so now we're going to get into the Linux subsystem. A little bit of history first. SPI Subsystem was originally created in the early 2000s. I think it was right on the cusp of 2.5 and 2.6. The subsystem came in, and these are the core developers that brought the system to life, major contributors to the device subsystem. And it all kind of came into place as the device model was formulated, essentially. Now, here's a few of the past maintainers. Sadly, David passed, and so Grant came in and was the maintainer for a while. But currently it's Mark Brown. He's the SPI maintainer. He's actually here, I think. So if you wanted to meet him, you might be able to talk to him in person. Okay. If you're going to be doing some real kernel development, you're going to want to get used to using the mailing list. And I grafted this from the SPI mailing, or the kernel mailing list, or major domo vjerk at .kernel.org. So what will happen is if you subscribe, it'll send you emails for everybody's patches and comments to the mailing list. I wouldn't recommend doing this unless you're a really serious developer, because you'll get a lot of emails. So especially if you go straight to the LKML, which is the top level one, yeah, it's unmanageable. But I do subscribe to a few subsystems. And the archives are online if the web interface is working. Sometimes they'll be down, but you can see the activity on the mailing list through the web browser on the archives. So if you're going to make an SPI adapter driver, which means the side that's inside of the chip, the host, then you're going to talk to the SPI mailing list, essentially. So controller drivers. So controller is the host side driver, and it it's used to abstract the hardware at the host side and provide a common API for the drivers that attach to the core, essentially. So this structSpy controller here, if you were to click on that link, you'll see that there's a lot of different fields in that struct. So a driver, we'll go a little into how the controller drivers work, but we're not going to get too deep into it because it's kind of out of the scope of the talk, because we want to focus on the other side of the bus of slave drivers. So here's the basic rundown of a controller driver. These functions, if you search for them online, you'll find them. They're going to be defined in the. You can find them pretty easily, or you can just go clone the kernel repository and grep form. But when you first create a controller driver, you want to do a SPI-ALEC or a SPI-ALEC master, and then you set some fields and set the some callback functions. The one that's particularly important after it's set up is transfer one message. You use either one or the other depending on your hardware. It's easier to use one versus the other. And I've actually transitioned from one to the other on the OMAP SPI driver, actually, in the when I added GPIO chip select support for the driver. Then you'll register the master, and it'll be ready to take on SPI devices. Okay, so we'll take a little short look at the device tree binding for the controller. First, you'll have your basic compatible string, which you're probably used to seeing now. Every driver will have a compatible string, which will match against, so it can associate to the driver. Then you'll have your address cells. That just tells you how many fields are in the address and what's in there, essentially. These two are optional: chip select GPIOs and number of chip selects. CS GPIOs are used to augment the controller if there's not enough chip selects for your specific needs. You can add chip selects using GPIO, and the core will handle toggling the chip selects for you when you're associated with that specific one. So that's a nice feature. And if you want to use some of the native chip selects and some of GPIO, you would either specify the GPIO or go ahead and just put 0 and it'll use the native chip select. I think I have an example. Yeah. So this is the one we're using, SPI1, and this is in one of the DTSI files, which are in the kernel source. So you'll see here, you have your SPI address, which is a platform or the memory mapped address. Reg tells you where that thing is in the memory map space physically and the size of the map. So there's a lot of controller registers in there. So they need this one particularly has a space of 400 hex. Then you have this interrupts, etc. Sometimes there's controller specifics, so that'll have the vendor's name on it or the manufacturer's name on it. Those fields are specific to that particular device. A lot of the times you'll have DMAs in the background, so you'll pass the DMA pointers and the names to the driver. Usually at the DTSI level or the controller level, they disable them by default, and then in higher layers in the DTS, you'll enable the SPI channel and add slave devices to it. So I'll give an example of that in a minute. Okay, so protocol drivers are essentially the drivers for the slave devices. And for each slave, you'd want to have a driver for it. Your protocol drivers will be spread out throughout several subsystems in the kernel. So it depends on what type of device it is. So if it's an analog converter or a sensor, usually you're in IIO or hardware mod. If it's a touchscreen controller or a keyboard emulator, then it'll be input. If it's a SPI flash, sure.
I'm sorry. Is SPI kind of similar to I2C?
Yeah, it is similar in some respects. It's a serial protocol, but there are some key differences. One being that it uses push-pull drives, and it is full duplex, and it's not multi-master, so you can only have one master on the bus. But it's very similar, yes.
Okay.
One other key difference is...
There's I3C that's coming up. There was a presentation during my talk.
Yeah.
About it. Yes?
I3C
so
is...
it's an extension supporting both I2C and SPI.
Yeah, in between. So really, SPI is kind of, it's similar, but it's different. You notice how with I2C, you'll have addressing that's part of the protocol. You'll send an address in the transaction, which will cause the device to read or write, depending on the byte that has the address and the read-write bit. Essentially, there's only one data line on I2C, whereas we have two on SPI. So you can go both ways, like in and out at the same time. It's not the same, but it's close. They're very similar. SPI can go a little faster too, up into the megahertz range. Yeah. Oh, can we get the mic up here? Scan the corner.
Can you just touch on, so it sounded like the controller side, I mean, obviously it's SPI. So now protocol drivers here, it's going to be speaking SPI. Is it like a higher level protocol on top of that? Or?
Well, yeah, it's the protocol for the specific device. So the host controller is just there to talk SPI. This thing is to talk the protocol of the device on the other side of SPI. So if you have a MTD flash, it'll know the protocol for talking to the flash. It doesn't have to worry about the host controller because that's all abstracted. So that same SPI protocol driver could be used from platform to platform seamlessly. That's part of the device model, essentially. Yeah.
Thanks.
When they talk about QSPI to like a flash, is that like
QSPI is quad SPI. It's an extension of SPI with
more data lines?
More data lines, yes. Okay, so messages and transfers are the key parts for creating a message that passes from the host to the slave, and we'll break that down a little bit with the slides. You have this structSpy _ device, which is passed to the probe and remove functions, which will pass information about the host, relevant information. And we're going to go over that struct a little bit too. Okay, so transfers are a single atomic operation between the master and slave, single operation between the master and slave. The RX and TX buffers are supplied to the transfer or for the transfer, and then you have the chip select option behavior of the transfer. And then you have message, which is a sequence of transfers that make a more composite message that comes across. And this is the argument to the SPI subsystem read and write APIs, which we'll go over as well. Okay, so here's the structSpy device. So there's quite a few things here, but this is a lot smaller than the other side on the controller side. So we can actually put it on one slide. If you can't read it here, you could pull it up on your PCs or your laptops. So there's a bunch of fields. The struct device. This is a generic device, and then you got the SPI controllers, the speed of the max speed of the bus, chip select number that you're using, bits per word, mode. This is all being passed to the probe function so that you can handle it essentially. And here's some fields that are used to set the various modes. So again, you'll see you can set the phase and polarity here, and you see how they have the modes ordered together there. So you can have you have just macros, so you can more easily set up the mode. SPI CS high is kind of an interesting one. Typically, chip selects are active low, but in some weird cases, you'll have a chip select that will toggle high when it's addressing. And yeah, you can have that, but it's not really friendly to the bus because most of them are driving low. So you can only have like devices. So you can only have devices that are active high on any one bus. And there's other oddball cases like SDMMC over SPI, which kind of just throws the chip select any which way. It actually performs transactions when the chip select's high and low, but that really limits the controller to one controller, one SD card, essentially, unless you do some really tricky stuff, which isn't mainline. Okay, oh, and you'll see there's your quad and dual SPI like you were asking about. Okay, so let's break down the probe function of the protocol driver so that you see how it kind of evolves. So you have your MySPI chips data, your platform data, which is platform data was kind of the old way of passing data from a platform file, which was an actual C file, and then they transitioned to device tree. So some drivers you'll see this P data thing, and if it's registered with device tree, it'll actually augment the local P data and use that so that it can use the same driver for both. Now here's an example of a device tree matching and setting of the platform data based on the matching. You don't necessarily have to use the platform data. That's not a requirement, but it just kind of evolved that way, and you'll see that a lot of times in the drivers. So when you have a compatible string that matches, then it'll match there, and it'll say if matched, it'll start doing all it'll read the parameters that are being passed from the device tree, and then kind of sets up some local state. Then you got your per chip state, so you could do an allocate, and we're using devm, which means it'll allocate, and then when it'll automatically free when you remove the driver, and then this SPI set driver data essentially passes that chip data so that you could retrieve it within the driver and use it essentially. Okay, so here's a look at the open firmware or device tree binding portion. So you'll see a struct open firmware device ID table in your driver typically, and then it'll have a list of compatible strings depending on the number of devices. You could have like several, maybe 10 even. Depends on the driver. In my company, would be the company of the device manufacturer, and your my SPI would be the actual device part number usually. This data here can be used to as a kind of a field to pass like a struct or some information to the driver so that it can initialize the controller accordingly for the different devices, whilst leveraging code reuse, essentially. This module device table here will put that one, and it's a macro that kind of expands out. If you're interested, you could search it and see how it's defined. So here's a regular SPI device table, and you'll see these in the device as well. And this is just, it's kind of the older way. And your SPI device will have a name and a type. It's really just for matching and instantiating the device. Okay. Now here's the structSpy driver. So this struct it has a handful of function callbacks, function pointers that will be called during probe, remove, shutdown, etc. And that device ID table is going to point to the table from the previous slide, and then you have your device driver. So here's an example of filling in that struct. So you have your driver, and you got your name. PMOps is for suspend, resume. Occasionally you have that, so you can shut down clocks when the device is in suspend. It's not a required parameter. Actually, neither of these are really required, but there's your open firmware or your device tree binding, which will take that table that we previously showed. And then you have the probe function and that regular ID table here. And then this module SPI driver will register it. Okay, so now I'm gonna go into the various kernel APIs, and these are what you're gonna use in your driver to access the device, essentially. So there's SPI async, which is a asynchronous message request, and callback is executed upon message complete. It can be issued in any context, meaning that it can happen in an IRQ context, but usually you don't want to do that. But then you have SPI sync, which is for synchronous requests, and you can't do this one in a sleep or a context that can sleep. So that one you just got to watch out when you use that one. It's a wrapper around async essentially, and then there's further wrappers around those, SPI read and SPI write, which will do the magic essentially. All right, here's a few other ones. SPI read flash, which is optimized for SPI flash commands. Not particularly useful unless you're talking to a SPI flash. Then you have SPI init message, so it'll initialize a message queue essentially, and then you add transfers to the message, and then do the API call essentially for read and write. So now I'm going to go a bit into the slave node device tree binding. So this is the part where you add your chip that you want to map to the SPI controller. So you'll have a compatible string, again, and you should be getting used to these by now. With everything pretty much has them in the device tree. And then you have a register, which tells you which chip select you're using. And then you have a SPI max frequency. So that'll tell you, with this specific device, don't go any faster than this frequency or it won't work. There's usually no lower bound, but the upper bound is important. And what happens is that'll take the controller will try to match that maximum frequency as closely as possible. They usually have prescalers which divide the clock, and then they try to match the maximum clock frequency. And this is in hertz, So when you do a registration, you'll have all the zeros, the trailing zeros. Okay, and then here's some more optional parameters so that you can set the modes. So you'll just have, since these are empty parameters, they'll just kind of be there on a single line with a semicolon at the end, and that'll tell you that I want to set that particular bit or field. And yes, so those will correspond one-to-one with those defines that we saw earlier. And then you have your bus width and your delays, which can be set for sometimes important for some devices. Okay, so now we have a slave node device tree binding. Okay, and again, you'll see my generic my company my SPI example. So what we're doing now, you saw earlier we had the controller registration. This is applying over the top of that, so that's why you have the ampersand. So it's referencing that specific node, and it's saying apply this piece to the top of that. So you'll have to enable using status equals OK, and then this pin control thing is to set the lines as SPI. I don't have an example of this, but I think he showed earlier pin control. It's basically just setting the boxes so that it's SPI pins instead of GPIO or whatever else they have on the lines. And then you have your driver compatible, your frequency, any modes that you want to set, and this register here is the chip select number. If you wanted GPIO chip selects, you would usually list them up here. Okay, so for historical reasons, we'll go over the platform registration. So it's just a struct that's passed, essentially. It's from a platform file. You fill it in and then pass it through. So you'll see the same kind of information being passed across. And here's an example of your SPI registration in the board file. We don't really deal with these much anymore, but it's here. All right. So that pretty much does it. I mean, this is the hardware that we have. Sorry. This is a GPIO expander. Oh, man. Excuse me. Whew. Oh, yeah. So you have your your SPI lines coming in here. Some GPIOs on the other side. And those are used to drive the LEDs, essentially. So this SPI GPIO controller is actually supported by the mainline kernel. So we can actually register that directly. For the labs, we're actually going to access this in a few different ways, kind of show the different ways of doing it. I have a demonstration of how to use SpyDev, which is a userspace driver thing, which isn't really encouraged beyond testing, but a lot of people use it, and they'll have SPI wrappers or function wrappers, libraries that'll use them, like libmraa, libsock. They'll use them, or maybe like Adafruit libraries, stuff like that. There's Python bindings and stuff. And then I'll go into kind of the standard device tree, or not the device tree, but the standard device driver. And then we'll look at the various pieces within that driver. I don't know what's going on. This happened to me last time too. I'm good. I'm good. I'll clear up in a second here. So you could map an interrupt, but we're doing outputs. There's no need to do that. So really, this one is going to be fairly practical. So we'll spend a lot more time in the labs. And if we get done early, you guys can go check out the showcase out in the plaza level. So I guess let's get down to it.
Do we want to take a quick 10-minute break?
It might be a good idea, actually.
Yeah, just a bio break and give everyone a chance to stretch their legs and such.
Awesome. And if you have questions about anything that I've done so far, just come find me.
Yeah, we'll take questions after the break.
So let's take a look at the SpyDev interface a little bit before I go into it. Before we compile it and try it out. It should be SPI_test in the repo. I think. I actually wrote this test a while ago, and there's I think 5 different SPI tests in the world that I found. They're all very similar. And there's a bunch of utilities that do SpyDev. You got to remember, this is not the preferred way. This is the way to do it when you first have a device and you have to test it quickly, essentially, before you make your driver. All right, so we'll go down. This is a regular user space program. It's not a driver. It attaches to a driver, and that driver is called SpyDev. BeagleBoard will actually, when you off the shelf, when you get them, they'll attach SpyDev to all the unallocated ports. So this should work out of the box, essentially. Other devices don't do that necessarily. And setting SpyDev in the device tree is actually not recommended. So this is it's a good way to demo and test, but it'll quack at you in the kernel messages if you register it. You probably don't have to worry about any of this. It's just basic code. But the important parts, let's see. Here we go. So like in the kernel side, we have a transfer struct, and it's got buffers just like in the kernel. These buffers are used to pass data out and then receive data in, and then you get some delays, etc. There's a way to set the mode and a lot of other things. It's not in this example. But essentially, this struct is filled in with fields from the command line, or with data from the command line, so that we can jam the protocol manually from the command line, and I'll show you how that works. It's just basic get ops long. So there's not a whole lot to it, as you can tell. You set up this transfer, and then you do down here. There's going to be an open, so you open the device node. So this will be passed, but it's a /dev device node. And then once you do that, it takes it and does this I/O control, and this I/O control will perform the message essentially. So that'll call to the kernel, and it'll do the kernel APIs in kind of a stub driver. It's not a general. It's like a general purpose driver. And then once it's done, we'll print out the transaction, and we'll see kind of the content of the transaction. So let's do the GCC to compile it. SPI under test.c -o, and then SPI_test to create the driver, or no, not the driver, but the user space demo. So then if you run that program without any arguments, it's going to tell you how to use it. It's pretty simple. So you pass the device node, the length of the transaction, the message that you're wanting to send out the MISO or the MOSI, and then the MISO will come back in a print statement essentially. So for this particular device, the GPIO expander, luckily the register is pretty easy to access. So you can do it, you can emulate the protocol pretty simply. So if you do a SPI test, SPI, okay, what did I get? Oh, this is like a for loop. Yeah, this is blinking LEDs. All right, so for our node is SpyDev 2.1. That means it's the second controller, first chip select, or second chip select because it's 0 indexed. This is the length of the transaction, so it's a 3-byte transaction. You'd have to look at the data sheet to understand how I got these numbers here. So the first byte is actually just an address for the specific device. The second one will have a read-write bit. So if I set this second one to 1, then it'll read. And then this byte is the address of the register internal. So I'm going to write the 0th address register, and then I'm going to hit it with a 55, which is just every other bit on and off. So it looks like it wrapped around, but if you type in .spytest, et cetera, et cetera, et cetera, and then we did the S-S is the speed. I just put in, it looks like 1 megahertz, and then you hit it, and the LEDs should turn half on, half off. Is everybody getting the LEDs to show up? Magical? And if you want to switch it to the other LEDs or turn them all on, you put FF here. Whoa. And you'll see them all off, I mean, because it's inverted logic. But essentially what we're doing is we're switching it from input to output, and when you set it to an output, it'll drive the LED on. But that's because we're using an open drain configuration. But so if you write a 1 out, it'll actually turn off. And then if you put that to 0s, you'll have all the LEDs on. So yeah, pretty simple. And this is really great for when you first start. You just got hardware right off the line, and you need to tell them, hey, this hardware is good, and we need to move on. This is great. But when it comes to production, you want to make an actual driver, or at least if you don't have one in the main line, make a new driver. And that's what all those Kernel APIs and stuff, etc., will use. So for the second part of the demo, we're going to use this thing. There's this SPI GPIO script here, and if you take a look at this script, I can kind of break it down for you to show you what I did. I don't know if did we show we showed use of device tree overlays in the previous one. So essentially, this will compile the device tree overlay from the device tree overlay source file or DTS file. And then it'll put it in the lib firmware directory, and it needs to be there for the kernel to load, or for the U-boot to load, depending on what you're using. So this sed command here does some magic, which it'll modify one of the lines in the boot U environment text file. So what it'll do is it'll switch over from some generic U-boot overlay address 0 equals something with a comment in front of it to uncommented with our device tree enabled, our overlay. So let's take a look at the boot U environment text file to see what it looks like beforehand. /boot U environment.txt. Okay, and pretty recently devicetree overlay port was added to U-boot. So you see this line here, U-boot overlay address 0. This is what's going to be filled in with our new entry. So if I go here, what we want to do is sudo, and then SPI GPIO shell, and put in your magical temporary password. Okay. So now what that did is it compiled the device tree overlay. It's SPI GPIO .dts. And what this does is, first it disables channel 0 and channel 1. What that was the SpyDev enumeration. So we're turning those off, and then we're going to enable our microchip expander, and that will give us the GPIO controller driver. It's actually in drivers pin control, and we'll take a look at that after we demonstrate it, essentially. This is a field that's specific to GPIO controllers, GPIO dash controller. That'll signal to the GPIO subsystem, hey, we have a new controller coming on board. The SPI mask allows you to daisy chain multiple of these chips, so you can make a lot wider bus with a single SPI channel in the chip select. You can have up to, I think, 16 or no, 8 devices, something like that. And then the register one is just that's the chip select, which we saw was what we used before. And then there's our SPI frequency again. So that's what we compiled, and it put that compiled overlay file into that directory in /lib/firmware. Now we can take a look at the U environment file that got kind of tweaked with that sed script. Doesn't look like it worked for whatever reason. Check on your devices and see if it actually worked.
Mine doesn't work.
It doesn't work? Looks like, well, we're going to have to do it manually then. So open the file and go to this line right here.
I'm sorry, what was the file?
Yeah, it's /boot /u capital E nv.txt. It's the U-boot environment. This is something specific to Beagle board, the way they do it. Okay, so you'll uncomment this line here. Oh, you gotta modify the file as root. Okay, take off the comment here. And then the name of the file was SPI-GPIO, I think, equals, like that. So everybody got it? I'll leave it here for a sec, make sure everybody gets it. So what this will do is it'll, instead of doing the config-bs overlay, this overlay will be applied in the bootloader so that it can actually happen earlier in the boot sequence. Everybody got it? Let's make sure that I got that name right. Yep, SPI-GPIO, all right. So now that that's enabled, what we're gonna do is reboot the system. I don't know why that sed script didn't work. Jason Kreidner added that after we did the last session, and I guess it just didn't work, or something's not right. So we're gonna let the system reboot. This will take a minute. We can watch it on the serial comm, I suppose. Oh. That's gonna, it takes a little while. I don't know what happened. There it is. Ha. All right, so now we're back. We can SSH back in or use the serial com if you need, or you prefer. Okay. Now, if you do an ls mod, you'll see the last entry there is the GPIO underscore MCP 23S08. So now we have an actual GPIO controller driver attached to the SPI bus. All right. So that means that if you do let's see, cat/sys kernel debug GPIO, it should list it there unless it's not mounted. Debug GPIO. You might have to do this as root. So yeah, you see there's GPIO chip 4, and it dynamically set the GPIO numbers from 496 up to 511. There's, if you remember, there's 16 outputs where you're doing 2 7 segments. So there's the first 7 bits and then skip a bit and then the next 7 bits. So you can turn on the LEDs individually by going into sys class GPIO, and then you have a GPIO chip 496 here. That means that we can export. So you echo 496 into, oh, you get, of course, we got to run this all as root, so we may as well drop into a root prompt. Okay. And then echo, oops, 496 into export. Okay. Now if we do an ls again, magically there will be a file GPIO 496. So you cd in, or it's a directory actually, cd 496. All right. So now we can individually address all of the LEDs. So if I echo out into direction, the LED will turn on. I should. Oh, and it's not. I put cat instead of echo. Sorry. There you go. So we have one LED on. Everybody sees that? Very cool, right? All right. So if you want to have some fun, go back to your home directory or CD, and then go back to the SPI drivers directory. There's a writedigit.sh bash script, and then you can say, okay, I want to write 1 2 to the display. Ooh. So you have to run it as root, and then you have 1 2 on the display. And if you take a look at this write digits, it's really just exporting those files manually, and then setting the bits accordingly and echoing them out based on a table. Pretty simple. So to kind of get an idea of all the concepts we presented in the slides, we can go back and look at how this driver, the various implementation details inside of the driver. Let's see if I can find it. If you want to get the source, the Linux source, I can show you how to do that as well. I don't think we've actually, in the course of the course, actually downloaded the kernel. Maybe tomorrow. I think there's a build root tomorrow. A build root and Yocto builds tomorrow. We'll do that in the background, essentially. Drivers. Pin control. Okay. Is that large enough, you think? You can see it? Okay. And then pin control, MCP. Oh, that's already open. And another COM. Okay, yeah, it's already open. So yeah, I can port on that one. Control plus. Whoa, maybe a little too big. Somewhere around there is good, right? Okay, so now we're going to actually see our SPI functions in action. This actually uses RegMap, which is kind of abstracts even further the SPI transactions, but we'll see the down at the bottom here. Let's go to the probe function. Okay, probe 1. It's going to call from probe. That's the I2C probe. There should be another one for SPI. I2C driver. So there's an I2C version of the chip. That's why there's both in this driver. But here's the SPI master driver. Okay. So as you can see, just as I stated earlier, you have your local P data, your local driver data. There's your open firmware match. So if you look at this table, that's going to point to the different devices. So you'll have your compatible string, right? So that'll say, oh, okay, I'll attach to that specific device. We're using the MCP23S18. So this is the string that'll match, and then that'll mean this data will be used when it's probed. Okay, and then if a match occurs, it pulls the data across into a variable, and then fills in the, since it was based on a platform driver or regular P data driver, they're augmenting the P data so they could reuse the driver code. But what they do is they fill in the fields with fields from the device tree. So this is a device property reads one of the nodes from the device tree to determine, you know, how many chips are on the bus. And that's pretty much, this will go through and add the chips. There's your allocation of the data. This one's a little more complex than my example, but you get the idea. And then you set the driver data, just like in the example. And then this is a bit more of a complex device. So it has like an auxiliary probe function that it calls. It passes the data through to that function, and this particular function will actually take either I2C or SPI function, or called from either one, essentially. Okay, and that'll set up some of the magic GPIO stuff, which really for us isn't that important for this, at least this this section of the course. I don't think GPIO is covered in the course. So now it does a RegMap init. Now RegMap init is gonna encapsulate the SPI or I2C bus and abstract it away. So when you do a RegMap init for SPI, it sets it up for SPI. But once that's set up for either SPI or I2C, you can use the same calls to access both types of devices. So then you have some more code reuse going on. So yeah, it's going to go through and do some magic, setting up the device. And then in here will be callbacks further up in the chart. Kind of hard to look at with this scrunched up screen. There's a register cache, IRQ setup. IRQ handle, mask, etc. Okay, so you see how it has a mutexes to disallow simultaneous accesses. So you want to understand how to do the IRQ stuff, or what do you want to know about it essentially? We're not using an IRQ. If you remember on the schematic that I showed earlier, because we're using outputs, there's no need for an IRQ essentially, but there is an IRQ pin. So if you did map that to a GPIO or pretty much any GPIO can be an IRQ on these systems. What'll happen is you'll map that IRQ in the device tree registration, and that'll be pulled across and be registered through the platform. And inside of the probe function, you'll see all the setup for it.
In terms of this driver, what's the purpose of an IRQ? What would be the purpose of an IRQ?
Yeah, well, it would be like a chained IRQ. So if it was set up as if the GPIO is set up as an input, you can say, hey, I want this input to trigger an interrupt. So, and you can actually mask in any of them as interrupts. So once you set it as an interrupt, the toggling of the line on the input will trigger an shared interrupt, essentially, that goes through that IRQ line, which is also kind of a shared interrupt in the controller for the GPIO controller. But it's kind of chained through, essentially. So you could trigger interrupts with a GPIO expander, essentially. Pretty cool. Yeah. And the interrupt code, I kind of glazed over, or I didn't really cover that great, but in your probe function, you'll have that set up. When you get down here, you have an IRQ that's passed from the main probe function. And then there's an IRQ callback function. That's not very easy to read, is it? So this will be the function that's called for the IRQ, and it's a threaded IRQ. So yeah, there's the request of the IRQ based on the interrupt that's passed through from the device tree, essentially. Okay, so I'm guessing we can. The lab portion's probably pretty much done. Let's see what else we got here. Sparkle, that one's fun. That just toggles the LEDs on and off really fast. So it looks pretty. Oh, it looks like permission denied, of course. Rude. And then you get some blinkies. Good for the kids or whatever. So last time, since I finished a little early, I actually took on questions about other functions, like if you wanted to light up the RGB LED, I could show you how to do that, or answer any questions about the various devices that are on there. So, got anything? Okay, we got a question over here.
So one question I had is, since we're going to walk away here, are you going to put some notes on what the lab's sequences were and get that into the tree so we can update later on? And
yeah, sure, we could do that.
Yeah.
I'll take some notes down and then post them up
just
for you.
even if it's like a little script, like what was in the
So you could follow along,
yeah,
or show somebody else.
Yeah.
Okay.
Yeah.
Yeah, and I think that the videos will be posted eventually, right?
Yeah, so just so everybody knows, I don't know if everyone's aware that there's a video camera here pointing at the instructors.
Good thing I didn't notice that.
Yeah, right?
Kidding.
And so we will be posting these videos eventually. There's the videos from Scale are actually already online if you want to see us doing it last week and being even less organized. But You're laughing, but yeah, we will have the videos both for scale, and then ultimately when we get around to editing these for ELC online, they will be linked on the main website rather. And just because I know that it's very difficult to get people to fill in surveys later, I always like to tell people early, there is a survey for what we've done here at ELC on the website. If you go down to the ELC section, there's a big survey link with SurveyMonkey. If I could get everybody to actually do that either today or tomorrow, we'd really appreciate that. Part of what we're doing here is the very first time we've done it. And from talking to all of you, it sounds like it's been very positive, but we'd like to hear about anything that you really liked or didn't like, what needs to be changed, what you'd like to see more, maybe topics you'd like to see. But anything you can do there then allow us to actually not only come back next year, but in fact go to other conferences. And so if you'd like to see us back or this kind of thing at a future conference, getting those numbers and those comments are very useful. So please do that. Otherwise, like I said, the slides will be updated over time. We will probably not get to it before tomorrow, in part because this is the 5th out of 6 days that we've been doing this with very little time in between. Quite frankly, there is a wonderful booth crawl that's happening right now. And I'm sure all of you would like to go see that and actually talk to the vendors there. And there's actually some drinks and other things available there, so that's very useful. We have one more day of slides and so on and so forth. We're only just publishing the slides for tomorrow afternoon because there were some major changes that happened there. Do keep on running that updater, and indeed, I imagine within probably a few weeks after the conference, once we've all gone through our notes and figured stuff out, we probably at least April before we've completely done it. So keep running the updater; it'll be there. Yeah.
Yeah, and I'll try to make actual like a walkthrough that's more verbose instead of these readmes that are just kind of slapped together, whatever I had before. So.
And this is probably the first time I've talked about this, so perhaps it almost becomes a promise if I say this, but. We've heard so many different really funny stories that have happened along the way. So many things have been done in such a short period of time that we're hoping to put together a bit of a blog post as to the journey that we took over the last few months, along with all the craziness that we've had to go through to make this happen. And so it should make an amusing read and perhaps explain some of the things that you've seen in the last few days.
Yeah.
But I would like to thank Michael Welling for his SPI talk. Hopefully you learned a bit more about SPI and how things work, and played with blinking lights and see how those things work. We will be using this board in future at future conferences and probably next year for all of our things as well. So certainly when it comes to taking these courses next year, if you already have the kit and we haven't changed the kit, you don't need to buy a new kit. So that works really well. The registration fee for these courses were literally to fund the kit. That's it. So we don't really care otherwise if you're in the room. It's just a matter of doing the practical part of it. Only really works if you've got something to do it on. Yeah. So in any case, we will come back tomorrow, finish things up. We're going to have a Yocto book to give away for free, much like the one that they're raffling right now at the Yocto booth. The schedule actually has our final talk going through the closing game. Now, who here has been to ELC before? Okay, so most of you have never been to ELC before. There is a game at the end of ELC called the closing game, and it's a tradition that's been started from the very beginning. It's one of those things where everybody gets together and they talk about what happened, and then there's prizes and games that you play for those prizes, and it's something we don't want you to miss because it's kind of
super fun.
It's kind of the whole point we're here. The rest doesn't matter. Friends and great topics, and it's the closing game. So we don't want to deprive you of that. So we're gonna do the lecture portion of the Yocto talk, and then we're all gonna run over to the closing game. So. Now, if anybody wants to work on things after that, we can certainly come back and mess around a little bit more. But I have a feeling that since most of your faces I've seen for the last 6 classes, I suspect everyone's probably pretty tired. So we're all going to be available via email, and at least one person has suggested a mailing list. We will try to put together a mailing list for all of you to ask questions and such. Again, we still have the G+ group. We have Twitter, we have IRC, but we will put together the mailing list. In order to be announced when that is available and updates and so on, if you could please go to the website and sign up for the, there's a big annoying pop-up that says sign up for announced mailing list. If you put your email address on that, we will let you know when these things are changed. So that's not the you know, the user forum kind of idea, but at least we can tell you when things are happening. We have no ways of reaching you at the moment. So in any case, the more of those things you do, the more we can basically send information to you. So
Yeah.
yeah.
And thanks for the compilation fix. That was awesome.
Oh, and of course, everything's on GitHub. So if you find bugs and you want to send patches or do a pull request or whatever else on GitHub,
Yes.
we've already had that from Scale. We've had several pull requests from Scale.
Community
already, so
effort.
Totally. So we're entirely happy to take patches. So
Patch is welcome.
excellent.